So in this video, we're going to talk about model selection. So this gets to the discussion we had, in the previous video about model complexity and whether it's a parametric model or a non-parametric model. And in either case, usually machine learning algorithms have the ability to tune the desired complexity of the model. So even though a non-parametric model can have arbitrary complexity, you still might be able to control what the algorithm is actually going to output, right? Even though the hypothesis space H is really big and contains really complex models, you can still probably have some settings that make the learning algorithm prefer lower complexity models. So then the question is, how complex do we want these models to be? And in order to understand that, we're going to have to think about ideas like overfitting and underfitting. We're going to have to think about generalization error, and we're going to have to think about validation as a procedure for model selection. So here's some scenarios you might think about. So suppose you have some training data and you run machine learning algorithm 1, right? So this is something that you don't know exactly how it works. You just downloaded it off the internet, and people say it's a really great algorithm, so you wanted to try it on your data. And then you run this algorithm and you get predictor 1, right? This is your predictor that gets output from the model, and then you run it on your training data. So you want to go evaluate how good this predictor is at the task you trained it for. So you go to evaluate it, right? You run it on the training data, and you get 0.02 accuracy. So it did really bad. Or well, actually, we don't know. Maybe that's actually relatively good. So okay, so that's fine. And then you go to deploy it. So your boss says, okay, I need this machine learning algorithm up and running on the website right now. So you go to deploy it, you get real world data, you run it on the real world data, and you get 0.25 accuracy. Okay, so that's not that bad. I mean, it's fine. Maybe 2.5 is good relative to like if you're trying to classify out of 100 different classes, right? Random guessing would be something like 0.01 accuracy, so 0.25 might be pretty good. But let's say you also try a different algorithm. So you downloaded this software package with another machine learning algorithm that people say is really great. So again, you give some training data and put it into this machine learning algorithm 2, and you get predictor 2. And then you go back and, again, evaluate it on what you trained on to see how well did it learn what it was trying to learn. So you evaluate it on the training data, and you get 95 accuracy, or 0.95 accuracy, or 95% accuracy. Okay, so that's a huge number. That's almost perfect on the training data. So you're really excited, and you go to deploy it to the real world. You tell your boss, like, get ready, watch this, and you hit go, you deploy it, and it gets you 0.27 accuracy, and everyone laughs at you. Okay, so right, what's happening here? And this is an example of the difference between accuracy on the data that you're training on versus accuracy in the real world, or the risk, which we talked about a few videos ago, is the generalization error. So in this case, we had a huge generalization error. The amount of error in our prediction of how well we'll do is which is, I don't know, 0.68, which is something huge if I did my subtraction right. So what's going on here? What's the difference between these? So let's say for the sake of again, this is just this wholly imaginary cartoon example, but let's say we want something around, I don't know, 0.5 accuracy, okay, or higher, and let's say 0.25 is actually not that good. So if that's the case, what is going wrong with both of these algorithms? So what is going wrong with each of them, or with the first one is it's underfitting, and the second one is overfitting. And what that means is that, right, when it's underfitting, what it means is that it's not the model or the machine learning algorithm is doing a bad job of fitting the training data. Right? Remember, it was getting only something like a quarter of the examples correct, and we should expect that if the model is of the right representation of the data, you'd be able to do better than that. So some of the reasons that can lead to underfitting are if the model is too low dimensional. Right? This could be a situation where we just designed a mathematical model where there just aren't enough knobs for the machine learning algorithm to tune to get a good fit. Or it could be that it's heavily regularized. And what that means is that I mentioned at the beginning of this video that machine learning algorithms generally have a tuning parameter that the machine learning user is able to select how complex you want to let the model be. And this is to sort of trade off between these two problems that we're showing right here. And if you tune that too high, if you tune the regularization too high, you're forcing the machine learning algorithm to try to produce an overly simple model. And when you do that, sometimes you underfit. And then lastly, sometimes even if you have that parameter tuned right and you have the right dimensionality, if your modeling assumptions are totally wrong and don't really reflect the real world or whatever is generating your data, then no matter how good your learning algorithm is, if the space of hypotheses doesn't even include a hypothesis that accurately models the data, then you're going to underfit. Okay, so then on the other end of the spectrum is when you have overfitting. So what happens there is that essentially, we saw in the previous cartoon example that we were getting 0.95 accuracy. So it was doing almost perfect on the training data. So in the absolute extreme, you could imagine a learning algorithm that just memorizes all the data. So it just memorizes all of your examples from a training set, and it will get 100% accuracy, right? Because it's memorized every example, and when you go to test it if you go evaluate your learning algorithm or the model the hypothesis that it output on your training data, it's just going to match it one-to-one to everything that is memorized. But now if it gets a new data example in the real world, or when you go to deploy it, or if you evaluate it on some test data, there might be a data point that's very similar to one of the data points you memorized, but is not exactly the same. And this memorization learning algorithm won't know what to do with it. So that's an example of overfitting, and it happens a lot in practice when you have high dimensional models, right? So a model that's very, very high dimensional, so there's a lot of parameters for the learning algorithm to optimize over or to tune. Or if it's non-parametric, right? If it's a non-parametric model, sometimes you can end up with overfitting. And conversely to the underfitting example, it might be that you're weakly regularizing this model. So where you had that parameter that you as a machine learner or machine learning expert could have turned this knob to be more complex or less complex, you set it to be super complex and it made it memorize the data. And another possible sort of cause for overfitting is that you're not making enough modeling assumptions. So this is something where you say, well, anything is possible, so let the machine learning algorithm do whatever it wants, and therefore the space of all hypotheses is way too big and way too nuanced, and the learning algorithm again is able to learn a model that does too well on the training data but doesn't generalize. Okay, and then lastly, sometimes this can happen if you don't have enough data. So all the other things that I talked about, right, high dimensionality, weak regularization, or not having enough modeling assumptions, a lot of times that can be remedied if you just have enough data. But the problem is if you don't have enough data, then you sort of then you need stronger modeling assumptions, you need stronger regularization, and maybe lower dimensional representation. So another example of this phenomenon is if you just look at fitting trends to numerical data. So a lot of times you see people look at numerical data and it looks kind of noisy. Let's say you're plotting this totally imaginary data on two axes. I didn't even label the axes because they don't matter. It's just numbers. And you see this as a human you can see this, look at it, and you sort of see a trend. And if you plot this kind of data in MATLAB, it actually gives you a bunch of options for data fitting. And one of the more powerful options is something called shape-preserving interpolation. And I'm not exactly sure what it does precisely, but you can see it's kind of interpolating between points, and then when points are too close together, it's taking kind of an average of the multiple points, and you get this very bumpy curve that pretty much pretty much lines up all the points, or it intersects almost all the points, except for when the things are really dense. And this, if you went and showed a scientist this plot and you said, well, look, I found the function that represents all this data that you collected, they probably wouldn't believe you. I mean, just as a human with our intuition, we can see that, this shape preserving interpolation method is basically trying too hard, right? It's basically trying too hard to fit the data exactly, and this probably doesn't describe an actual trend in reality. And then on the converse, right, this is an example. The green line, this shape-preserving interpolation, is an example of overfitting. And then the red line here that I've just added to the screen is a linear fit. Right, this is the line of best fit. One of the most canonical and most used methods of analyzing data in science is to do a linear regression. So this is the red line is the linear regression on this data, and again, human intuition is going to allow you to look at this and say, well, this doesn't look right. That I don't really think. I mean, okay, so here's what a lot of times happens in some of the less prideful moments in science, where a lot of scientific results have been, let's say, inaccurately reported, is where you plot something like this and you do linear regression, and you say, oh well, there's a trend going up to the right, and maybe that might mean that some dietary trick leads to, I don't know, reduction in disease, and of course, if you look at the data, you see that, okay, there's no actual trend here. And what you realize is that if you do something kind of in between the two, that's a little bit more powerful than the linear fit, which is underfitting, and a little bit less powerful than the interpolation, which is overfitting. You can do a quadratic fit, and it looks pretty good. And it turns out that I actually generated this data by taking a quadratic function of a noisy quadratic function. I cheated by setting up this problem so that I knew exactly the model class that we're looking for. So again, this is all based on human intuition. We can just look at these images and figure out what we think fits better just by looking at it with the eyeball test. But how do we do this more systematically? Right? We can't just always visualize everything. I mean, some of these things are in high dimensions, so it's hard to visualize. So we can't just always depend on visualization. So what's a procedure for us to choose between, let's say, these three models? So to think about this, let's switch gears, and let's think about the classification problem again. It's kind of easier to think about, at least for me. So I mentioned this, the nearest neighbor classifier as an example of a non-parametric model, and it turns out that that kind of crazy example I gave previously of like a machine learning algorithm that just memorizes the data. That's exactly what nearest neighbor classification is. Well, not exactly. That's the foundation of nearest neighbor classification. And what it does is it basically stores all the data that it sees and remembers what label that data had. And what it will do is when it gets a new data point, it will decide what example is this most similar to. Is this new input example most similar to? And what you'll find a lot of times if you use nearest neighbor classification is you're definitely going to overfit in some sense, because at least for pure nearest neighbor, you can make this less powerful if you do k-nearest neighbor, and that actually helps you reduce overfitting. But if you just use nearest neighbor, so just it finds a single nearest neighbor, you always get 100% training accuracy. Right? Because again, the nearest possible example is always going to be the true example, the original example. But let's say you get a new 5 or a new input that looks kind of like a 5, and that's not actually in your data set. It's going to then, try to match it up to things that look kind of like it, like 5s and 6s. Maybe it looks like an 8. Maybe it looks like a 3. So a lot of times you see something like this where you actually get a much lower testing accuracy than the training accuracy. So one way for us to not be shocked by this when we go to deploy our machine learning or our models that we learned from our machine learning algorithm is to do held out validation. So that's where we say, all right, let's take our training set and let's just sacrifice some of that training set, right? We originally had, in this case, 50 points, 50 examples of digits. Well, let's take 10 of those digits and set them aside. Okay, and then we're going to train on the 40 digits that are left over, and never look at the held out data. Never look at that last 50 or last 10 digits that we held out. And what we'll do is we will then train on the remaining data, and then try different models. We can then try different models using this data, and then evaluate it on the held out data. And what we are trying to do here is we're trying to simulate the experience we would have if we were to train on all our data and then just go and deploy it, and then bank all of our our money on some untested algorithm. Right? So in this case, we can test it in the simulation environment. And what we might see is something typically that looks like this. So we usually see a simple model that does reasonably well on the training data, and does kind of bad on the test on the validation data. We might see a medium complexity model that does even better on the training data, and then also does better on the validation data. And then we might see a complex model that does really, really well on the training data, but then does even worse on the validation data. And then lastly, we might see a super complex model where we can just completely memorize the training data, and we do terrible in the validation. So that's the usual pattern you'll see when you go to do this. And this is also not super robust, because we're sort of depending on the one set that we held out, that validation data on the right, to be representative of what our experience will be when we go in and deploy the machine learned hypothesis in our real world system. So instead, we can actually sort of repeat this process over and over again with different folds, as they're known. So we'll hold out the first 10 digits, and then train on the rest of them, and then we'll hold out the second, and then we'll train on the rest, hold out the third, and train on the rest, etc., etc. And this way, we at some point we will be using every data point as a validation example. And you can choose how many folds you want to do. You might only do 2 if you're lazy, or if you really want to be exhaustive, you can do n folds for n data points, where you are leaving out only one example. You train on all n-1 examples, and then you evaluate on that one example. And you're only going to get your accuracy at that point will only either be 1.0 or it will be 0. But then what you do is you keep doing that for all the different examples, and then you take the average, or you take some statistics of how often you're correct on leave one out cross validation. So at this point, it's probably useful to think about. I mentioned that you can start with. I showed examples of 5 folds, and I showed examples of n folds for the leave one out. I said you could do 2 folds. So how many folds should you do? So you should think about what are the pros and cons of leave one out cross validation, and relatedly, why would we be interested in different folds, using fewer or more folds? And then secondarily, another question you might wonder, and we should discuss in class, is, well, so I've described so far that what we're going to do is we're going to take n folds, and we're going to hold out one of them and train on n-1 folds, and then evaluate on that one held out fold. And that gets us, a small fraction of evaluated points and a large fraction of training points. So I presented it this way because this is usually how people do it, but there are also advantages. There may be advantages to doing it the other way, where you train on one fold and you test on n-1 folds. So let's think about what the pros and cons are between that distinction. Right, so you might want to switch things. Okay, and for experiments, when we're not talking, so I've been giving this sort of story where you're working in some industrial application and you want to deploy the algorithm, or deploy the predictor that you learn, or the model that you learn from your machine learning in practice. But when you're doing scientific research, or if you're doing research on machine learning itself, usually what happens is you have a big data set, and you just want to evaluate how well does my machine learning algorithm do on this data set. And the best practice is that you will split the data into a test set that is completely hidden from training, and then you'll use use validation or cross validation or leave one out validation on the remaining data. So there's actually like at least three splits. There's the training data, there's the validation data, and then there's the test data, and you usually rotate what the training and validation sets are. And this way, you have this set of testing data that is you never touch with your training process. Now, sometimes people will just report cross-validation score to show how well their machine learning algorithm is, but it's not the ideal thing to do. In particular, when you're using cross-validation to decide between models or tune a particular model parameter, like a complexity parameter. Okay, so in class we're going to talk about a couple things. We're going to think about different scenarios. So these are situations that happen every now and then in research or when you're going to try to run a machine learning algorithm, and they're kind of puzzling. So it's important for us to think about them and discuss them together and try to understand what it means when these things happen. So the first scenario I want you to think about is, what happens if you run cross-validation and you try cross-validation on different values of some complexity parameters. So you're choosing how complex you want your model to be, and it turns out that as you tune that complexity parameter, you get really erratic scores. So you just get like in this plot here, you get, for one setting you get 0.8, for one setting you get 0.9, and then as you increase the parameter a little bit, you get something like 0.2, and then it goes back up to 0.9. You see some really, really weird behavior. So let's think about what does that mean when that happens. And then the second scenario is if, let's say, the cross-validation is nearly uniform. So you tune your complexity parameter, and your score from cross-validation just seems to be basically the same no matter what you set that parameter to. So what do these things mean? Are there remedies for these situations, or is there something that we know has gone wrong? Okay, so to quickly summarize, validation is this fundamental idea in the process, in the methodology of machine learning, which allows you to measure performance by holding out training data or holding out the available data. And what the goal is basically to simulate the testing environment, simulate the process, the original process I showed you, where you train your machine learning model on your training data, and then you just go and send it out into the real world and hope it doesn't bankrupt your company. So the idea is you're going to rotate folds of held out subsets, and you can even hold out one at a time, so that would be leave one out validation. And you can use this cross-validation on your training data to tune extra parameters.